Pranav, are you speaking? Pranav.
Wrote the Jacobian of q. By definition, I wrote the velocity of q, which is jq times omega. And the question is, what's the intuition behind jq? Let me write the formula for Jacobian of q, and then we can talk about the intuition. So jq, after using the formula I just wrote down, comes out to be something like this: minus L sine theta 1 plus theta 2 plus sine theta 1. This is the first row, first column. And then we have minus L sine theta 1 plus theta 2. And then we have L cosine theta 1 plus theta 2 plus cosine theta 1. Then L cosine theta 1 plus theta 2. Okay, so that's the formula for JQ, and we said VQ is JQ omega, where JQ is given, but omega is simply theta 1 dot, theta 2 dot. Okay, so the way you can think of Jacobian is, I'm just going to write the elements J11, J12, J21, J22, theta 1 dot, theta 2 dot. So the way you can think of the Jacobian is, put theta 1 dot equals 1 and theta 2 dot equals 0. And so if you put that, you get, since this is 1, second element is 2, we have J11 and J12. Right? So it's just saying that the velocity of Q in the x direction is J11, and velocity of Q in the y direction is J12. Okay, let's just take this example. Let's put theta 1 equals 90 degrees. Theta 2 equals, we just keep theta 2 as it is. So if you put that in the formula in the JQ formula here, we get J11 equals, you can see here it's minus L sine 90 plus theta 2. Or better, let's just put 0, it's easier. So sine of theta 2, sine theta 1 is 0, and then J21 is L cosine theta 2, and cosine of theta 1 is, cosine of 0 is 1. Okay, so let's draw this situation. So we have theta 1 is 0, so that's what it is, and theta 2 is the angle, or is this angle? Okay, so what this is saying is that the velocity of point Q has two components, one in the y direction and another one in the x direction. And so if theta 1 dot, which is the angular velocity of link 1, is 1 unit, then VQX is J11, VQY is J, I made a mistake, I think this should be J21, is that right? The formula is right. J21, J11, and J21. Okay, which is minus L sine theta 2. Sorry, I switched it. It's 1 plus cosine theta 2 L, and then J11 is minus L sine theta 2. So if you keep theta 1 equals 0, theta 1 dot equals 1, then the velocity in the x direction is going to be minus L sine theta 2. So it's going to tend to go towards the left side, which you can see if you actually construct the two link pendulum. If you can hold your hands together in such a way that looks like a pendulum, and then you think of how will this move, it will start moving something. Yes, it just depends on the angle. So let's just make it even more simple. Let's just make theta 2 is close to 0. So what we can do is, so I just making it even more simple so we get the intuition right. So I'm going to do this and then make this very small. Same thing. Theta 1 dot equals 1. And then we can say that VQX is now minus L theta 2, because theta 2 is close to 0 or theta 2. And then for the other one, we have cosine of 0 is almost 1. So it's going to be 2L. J21 is 2L. So this is saying that when theta 2 is small, the velocity of this is almost 2L. It's going to be in the positive direction upwards, while this one is going to have a velocity this way. So this is minus L theta 2. Okay, and so that sort of agrees with intuition. In fact, when theta 2 equals 0, you can see that this link is parallel, and then the velocity of q is going to be only in the y direction. So this is how you interpret or you understand what is j by assuming theta 1 dot equals 0. Theta 1 dot equals 0. Theta 1, you just have to put theta 1 dot equals 1, theta 2 dot equals 0. Then velocity of j11 is going to be the velocity of q in the x direction. J21 is going to be velocity of q in the y direction. Similarly, if you want to find the other two components, then you have to put theta 1 dot equals 0, theta 2 dot equals 1. So remember that is vq equals j11, j21, j12, j22, theta 1 dot, theta 2 dot. So if you put theta 1 dot equals 0 and this equals 1, then you see that vq in the x direction is j12 and vqy equals j22. And that's how you interpret j's j12 and j22. So you need to basically put these special cases to understand what the j's really mean. Is that
Yeah, that's helpful. That
reasonable?
is definitely helpful. And we can see in the case where you chose the previous case that we just have our simple.
Is that okay, Jim?
Yeah. Can you hear me?
Oh, okay, hold on. I have a technical problem here. Sorry about that. I couldn't hear you because I was mute. Yeah.
Okay, can you hear me now?
Yeah, I can hear you. So that's how I this is the explanation I've seen before, but is that reasonable?
Yeah, that is helpful. And I think what is especially helpful in the previous example, when you chose theta dot 1 to be 1 and the thetas to equal 0, we can see that that just breaks down to a case from simple rotational motion from like high school physics,
Right,
changing angular velocity to the velocity at the point.
right. Yeah. There is a derivation in the book by J. Craig on just F. So the first part. Okay, and the force F acts at right angles to the second link. It's always 90 degrees. So as the link theta 2 changes, theta 1 changes, F is always 90 degrees to link 2. Write an linear expression for the force F in fixed frame. So this force is, if you write force F in, so this is frame 0. This is, sorry about this is x1, this is x0, y0, y0, y1, y2, x2. Okay, so if you write the force F in frame 2, that is basically F along, if you like to call this the unit vector along x2 and x1, then it's going to be 0 along x2. This is x2, and F along y2. So it's always pointing in the y direction, and that's why its value is this. Now you need to find a force in frame 0, in this frame. So we write something in the x direction, something in the y direction. The question is what are those components? So you can technically take F, resolve it along the x direction and the y direction and solve it. So if you do that, you just need to find the angle made by F with the horizontal. So if you see this, the angle between this link and the horizontal is θ1 plus θ2. If that's the case, then this angle, which is the angle made by this with the horizontal, is going to be 90 minus θ1 plus θ2. So this is 90 minus θ1 plus θ2. And then if you want to find the force in the x direction, let me write it down here. F0, it's going to be F cosine 90 minus θ1 plus θ2 along x0, and then F sine 90 minus θ1 plus θ2 along y0. But I think they missed the sign. This is going to be positive in, so it's going to be positive in the y and negative in the x, so it should be negative. Okay, that's one way to do it. There's another way to do it, which is probably simpler. So this all works nice if you are, if you can visualize things and write forces by looking at the angles, but many times it's not possible to do that. So in that case, you can use the same notation we used in the past. If we have a vector in frame 1, and if you want to find how it's related to the vector in frame 2, sorry, my bad, v0, you want to find how the vector looks in frame 0 compared to frame 1, then you just do r1 0. And then if you want to find the vector in frame 1, sorry, frame 2, then you just do r, see, r1 0, r2 1, v2, and so on. So this is how the formula we developed for rotation. So you can use the same thing, which is f0 is r2 0, f2, but r2 0 is r2, r1 0, r2 1, f2. And so if you know the rotation matrices, it's cosine θ1 minus sine θ1, sine θ1 cosine θ1, then cosine θ2 minus sine θ2, sine θ2 cosine θ2, and then the force, which we wrote down in frame 2, it's x is 0, y is f. You should get the same answer as this. Is something which needs to be checked, but that's the simpler way of doing it, which doesn't really involve any visualization and so on. So that's part A. Part B is asking for torques, which you can do, as you noted, by using a free body diagram. So torque 1, so torque 1 is going to be the r, the vector r from O all the way to Q, cross with the force, which now you need to write the force in the world frame. You can't write force in the local frame, and so that should give you the torque at Q. But hold on, so this should be with respect to, this vector should be from O to Q, so it should be OQ cross with F0. And then if you want to find T2, it's going to be the vector from P, so PQ cross with F0. That's one way to do it. Well, this one doesn't require any visualization either. So if you know F0, then you can just, if you know the positions of PQ, and you can do this That's one way. But the other way to do it is to actually write the torque 1, torque 2 is simply the Jacobian of Q transpose times F in frame 0. So so the other way to think about this, and I will leave this as an exercise, is clearly the Jacobian is giving you this part.
Mhm.
Uh, uh, so it is clearly giving you that part, and that's what needs to be checked. One way of doing that is, I don't know if you know this, but there's a property of skew symmetric. So there's something called a skew symmetric matrix. Skew symmetric matrix. Okay, all that is to a skew symmetric matrix. It has a special form. It has the form is 0, 0, 0 on the diagonals, omega x, omega y. We just make it ax, ay, az, ax minus ay, az, and it has a property that s plus s transpose is 0. So you take the transpose summit. So that's one property. But the good thing about a skew symmetric matrix is that if you take a vector A cross B and you write it down like this, I, J, K, AX, AY, AZ, BX, BY, BZ, and you take this cross product, or you can use in MATLAB, you can use cross AB, it will give you the cross product. It turns out you can also write it as S of A. This should be called S of A is this. S of A times B. So now what you need to do is you need to write S of A, which is the same thing I wrote down there. 0 minus AX, AY, 0, sorry, AX, 0 minus AZ, minus AY, AZ, 0 times B. So BX, BY, BZ. So if you do this cross product, you will see that it is going to give you the same answer as that. So you can take a cross, A cross B, and write it as S of A times B. So now, and this I've never tried, if you have OP, or the OQ, crossed with the vector F, so this is the torque 1, but you can also get the torque 1 using PQ cross F0. And then if you also know that torque, which is torque 1, torque 2 equals J transpose times F0, it seems like you have to use the skew symmetric form of this thing here. Just like it's over here, A
Mhm.
cross B is the same of S of AB. To write this, so it seems like you will get something similar. The question is, I've never tried this to see if that's true, but there's clearly a relation between taking the cross product and the Jacobian, which we also saw here in the velocity. Velocity is, one way of writing the velocity is omega cross r. But we also saw it can be written as J cross J omega. So there's something about taking this cross product and putting into J, which we also see here. Torque is the dual, I guess, is this. Torque is R cross F, but torque is also equals to J transpose F. So there seems to be something about cross R which manifests itself right here. So when
Mhm.
R cross, it becomes J transpose, and then when it's cross R, it becomes J. So they are somehow related. I've never seen somebody really work out this, but it seems that it should be through the skew symmetric matrix. The skew symmetric matrix helps you to convert two vector cross product of two vectors into a multiplication of a matrix times a vector. So this is vector vector, which is here, and this is matrix vector, matrix vector, which is here. So it seems like there's something to do with the second form here, and this is to do with the first form. So the question is, J is going to give you some kind of momentum, I think.